So this video introduces the inverse hyperbolic functions. As you'll see from the table, we have y equals r sine of x, r cos of x, and r tan of x. Notice that there is no c between the AR and the sine, cos and tan. So these inverse functions can be defined in terms of logarithms and are found in the formula book. And you can use them directly in questions straight from the formula book. In terms of the reasons for the restricted domains, let's have a look at the graphs. You can see that the inverse of hyperbolic sine is a one-to-one function, therefore no restrictions are required. The inverse of hyperbolic cosine requires the domain to be restricted and only part of the curve to be used. So if you think back to the graph that we had for hyperbolic cos, it was a many-to-one curve which has to be restricted to one-to-one in order that the inverse exists. Hence we have this graph here. And then the inverse of hyperbolic tan, the x values are restricted by the values that match the asymptotes that we had on the original hyperbolic tan curve. Okay, so we're now going to do the questions 1 and 2 on page 40. So question 1, we are being asked to derive the result for the inverse of sine. So we have y equal to the inverse of hyperbolic sine of x. That allows us to write that x is sine of y. And now we can move to using our definition. So we have e to the y minus e to the minus y over 2. We're now going to multiply that through and simplify it into a quadratic. So we have 2x equals e to the y minus e to the minus y. Multiplying through by e to the y so that we deal with the e to the minus y. We obtain 2x e to the y equals e to the 2y minus 1. And that simplifies to e to the 2y minus 2x e to the y plus 1 equals 0. Now you can see that we've got a quadratic, but the format of it with the coefficient of the e to the y being 2x is going to make it difficult for us to factorise. Our technique in order to derive the required result is therefore to solve by completing the square. So let's complete the square. So we have e to the y minus x all squared minus x squared minus 1 equals 0. I'm now going to solve for e to the y. So e to the y will minus x all squared will equal x squared plus 1. square rooting both sides and taking the x across, we get e to the y equals x plus minus the square root of x squared plus 1. Now, I only need to consider the positive square root, and we'll just consider y in a moment, but let's finish off the working here. I want y, so we'll take logs of both sides, and that gives me the log of x plus the square root of x squared plus 1. Hence, y is the inverse of hyperbolic sine, so I have arrived at the required result. Just one thing we need to consider, and that is why I don't need to include the negative square root. So let's just put a note. If I think about this, x squared plus 1 square rooted is always going to be greater than x. So if I were to take that away, that would give me a negative value here. But we know that e to the y has to be greater than 0. So we therefore do not want to take away a value because we will not get a valid answer. And therefore we only use x plus the square root of x squared plus 1. So that's the method for deriving the inverse of hyperbolic sine. Now we're going to go on and do question 2, where we are just going to use the results straight from the formula book. So we're being asked to find the inverse of hyperbolic sine of 1. So subbing directly into the formula from the formula book, and that's 1 plus square root of 1 squared plus 1 gives me a result of log of 1 plus root 2. And I can do likewise using the appropriate formula for these two. So we get log of 5 plus square root of 5 squared minus 1 gives me log of 5 plus 2 root 6 and a half times the log of 1 plus a quarter over 1 minus a quarter, which simplifies to a half the log of 5 over 3.